Kullman, who will be talking about control of autonomous electric fleets for ride-hail systems.
So real quick, has anybody not used one of these services like Uber or Lyft? Yeah, not one hand. So everybody's going to be pretty personally familiar with the concept that we're talking about today. So there's three sort of modern phenomena that are coming together right now in the field of transportation. This explosion in the popularity of ride-hail services like Uber and Lyft, the dawn or near imminency of autonomous vehicles, and the electrification component. And so these three things are going to combine to perform, to converge to this problem, or at least a problem variant that has not yet been sort of exhaustively covered in the literature. So I'm going to be talking about this problem today. This is work that I've done under the supervision of Jorge Mendoza and Martin Cousineau at HEC in Montreal, and Justin Goodson at St. Louis University. And so in order to solve this problem, we're going to be using a combination of techniques. So we're going to be using some policies developed using deep reinforcement learning, and that's going to be for the dynamic version of this problem. And then we're going to draw on some more classical tools, some math programming, to establish a bound for how good we're doing in the dynamic problem. So quick teaser before we really jump in. We've had some success here where the policy that was informed using deep reinforcement learning is outperforming our comparison heuristic by a little over 19%. So we'll get there. But why are we studying this problem? Why is this something that we're interested in now? So in 2018, there were on average 15 million rideshare trips per month in New York City. And this has been part of this trend. And so this continues to be an increasingly popular way for people to get around. And at the same time, the rise of electric vehicles is promising, given the current state of our climate. And these vehicles bring their own set of constraints, some additional constraints that are not present with conventional vehicles. And autonomous vehicles, I think, are right around the corner, perhaps a little bit closer than we give them credit for. So what we're looking at here is an image of Waymo's fleet. So Waymo is the former Google self-driving car. They operate a fleet down in Arizona today that the public can use, and these are autonomous vehicles. So there's a backup driver that intervenes occasionally, but the majority of the miles are covered by purely autonomous driving. And at the same time, Tesla thinks that they will start receiving regulatory approval for fully autonomous driving perhaps as early as next year. And when that happens, in these markets where they've received regulatory approval, you can imagine that there will be an over-the-air software update, and the next morning, people will wake up and be able to tell their cars to take them to work while they fall asleep, or watch Netflix or whatever. And they've announced that when this happens, you have the option to deploy your personal vehicle as an autonomous electric taxi during the day when you're not using it. And there will be some revenue sharing between the vehicle owner and Tesla. And I imagine that if you have the opportunity to use your car that's currently, or would be, sitting idle to start earning you money during the day, this is something that's going to be attractive. And so you can imagine that if this regulatory is pushed and there's a software update, all of a sudden, the next day, you might have a fleet of tens or hundreds of autonomous electric robo-taxis. So, potentially in 12 months, the next Informs, some of us will be arriving by autonomous taxi. Who knows? But how is this different than the situation that we have today? How do these types of fleets differ from something like Uber or Lyft? So right now, there is still some central control, but there's still control at the vehicle, right? So drivers can decide when they enter or leave the fleet. Drivers decide when they go eat. Drivers decide if they don't want to pick up the guy who is carrying a bloody chainsaw or whatever. Whereas in the future, your autonomous electric vehicles, they don't eat, they don't need bathroom breaks, and they don't perform any of their own decision making, right? This is all centrally controlled. So what are the decisions that one would have to make if they want to operate a fleet like this? So there's really just two things. The first of them is the assignment of vehicles in your fleet to the new requests, and the other is the repositioning or rebalancing of your fleet so that you can serve future requests. So if we just look at a simple example of what we're talking about here with a single vehicle. So a new request pops up and the operator says, okay, I'd like you to serve this request. So the vehicle does, but when he's done, he's now farther away from this region of demand. And the operator would like to move him back closer to this demand, but because his battery is low, he receives this instruction to charge at the nearby charging station. So he charges here a little bit, And then the operator says, okay, now I'd like you to get a little bit closer. And he moves him here, and now he's in a better position to serve the demand than if he'd been left originally. And this is the sort of control that we're hoping to do for a sizable fleet of vehicles. So we argue that there's sort of three primary problem components that are important to provide a meaningful solution here. So the first of them is real-time decision making. So we're all already accustomed to receiving a near immediate response from services like Uber or Lyft for which vehicle is going to come pick us up and how long it's going to take. And then it's also important to consider the fact that these vehicles are electric. So eventually we'll get to a point where charging happens rapidly, perhaps at the pace of you can refill your gas vehicle. But right now these vehicles are still taking hours to go from empty to full. And so you can't really just sweep that time under the rug. It's sort of a dangerous assumption. And then also, sort of from experience here, the more realistic your instances, the better, right? So we've had some success with methods on the unit square with uniform demand that certainly do not translate to a market like Manhattan, where you have demand that is certainly all over the place, non-uniform, and changes throughout the day. So I'm going to just sort of blow through the literature review and just say that for the most part, most existing studies ignore the fact that these vehicles are electric, and we'd like to make sure that we take into consideration all three problem dimensions here. So on the model and methods. So I mentioned that we're going to be using deep reinforcement learning to solve the dynamic version of this problem, and then we're going to be using operations research tools to establish a bound that tell us how good we're doing in the dynamic context. So we're going to start off by talking about how we solve the dynamic version of this problem. So we model this as a Markov decision process. We have an agent that's interacting with some environment. And this agent receives an observation of the environment, which we call the state. This consists, for our problem, of the time, the current time, vehicles' locations and charges, and any jobs that they've currently been scheduled, as well as whether or not there's a new request and where that request is. From a state, the agent selects an action, and here I mentioned this is the assignment of vehicles to new requests and repositioning and recharging instructions. And the actions that you have available to you depend on the state, right? So if a vehicle has a very low battery, it cannot be assigned to travel across the map. So we make sure that actions are energy feasible. And we also make sure that if we're assigning a vehicle to a new request, that we do this in a time feasible manner, which means that we want to make sure that the vehicle that we assign to that request can reach the customer within some short amount of time, say 5 minutes. So when the agent chooses an action, it then receives a reward from the environment. Here, the only rewards that we experience are the values of the trips that we're serving. So when we assign a vehicle to a request, we earn a reward equal to the like a sort of your standard taxi fare, where you have a base rate plus a rate that depends on the distance of your trip. And then in addition, the agent receives the next observation of the environment. So given that your initial state and then your action, what is the next state? So we update that. And this process continues, the state, action, reward, next state, until the episode terminates, which we set this as a finite horizon problem. So at the end of a day, we kill the episode. And our agent's objective is to choose actions in such a way that we maximize the expected revenue over a 24-hour period, right? So our objective is to develop an agent that maximizes the expected sum of rewards. So let's talk about the agents that we developed to solve this problem. So we built 4. The first 2 are fairly simple, and then we have 2 that use deep reinforcement learning. So the first one's just a random agent, chooses actions randomly at every state. The second one is, it's a heuristic we call nearest. It's pretty simple. If we have this situation here with a new request and a couple charging stations, we assign the closest vehicle to serve that request, which in this case is the red one. And then for the repositioning and recharging instructions, we perform a charge check. And if a vehicle's battery is below some threshold, then it's instructed to locate to the nearest charging station and charge. Vehicles that are not below some threshold then are just told to go to the nearest charging station and idle. So the third agent, the first interesting one, so for this agent we call it assigner because it uses a neural network. We use deep reinforcement learning to learn the assignment part of the problem. So what we're going to do is we're going to leave all of the repositioning and recharging instructions to the the same logic as the nearest heuristic, but we're going to use a neural net to figure out which vehicle to assign to new requests. So given this same situation, our agent has these 4 possible actions. We can either reject the request, perform no action, or we can assign the yellow, blue, or red vehicle, right? So you can imagine that our vehicle wants, our agent wants to assign, wants to choose the best action, right? But how do we know what the best action is? And so we're looking for the value of an action, and this value is known as the Q value, and this is the sum of the immediate reward plus the expected sum of rewards through the future until the end of the day as a result of choosing this action. So our agent wants to choose the action with the highest Q value, but how do we actually know what those Q values are, right? It's not like our agent begins with some knowledge of knowing that, for instance, assigning a vehicle will earn it more reward than not. So it has to learn these Q values. So how does this happen? So we basically, we run our agent in this environment, essentially choosing actions randomly for a long time. We collect a whole bunch of these memories. What state was I in? What action did I choose? What was the reward I received? And what was the next state that I landed in? And we're going to occasionally draw on those memories to update our predictions. What did I think was going to happen and versus what did happen? And then we're going to train a neural network on these memories in order to improve our predicted Q values. So what does this thing look like? So I'm going to basically not really talk a whole lot about this, but we use a neural network which produces, for some representation of the state, we get a scalar value for each possible action in the action space. And we're taking that general structure, and then we're implementing a handful of tricks that are known as the reinforcement learning rainbow, coined by some guys in Google's DeepMind team. And so if you have questions about this, please ask me. I'd be happy to talk about it. Okay, and so then our last agent, we call the full control agent because it's now responsible for everything. So this agent not only chooses vehicles to assign to requests, but it also chooses the repositioning and recharging decisions for all of our vehicles. And it's built basically the same way. It's still a deep Q network, plus this handful of tricks known as the reinforcement learning rainbow. But obviously there's some differences in the input state and the output action space. So for the action space, we are now performing a prediction for each vehicle in our fleet, right? So we're performing a per vehicle prediction where we have a Q value for the no op, the do nothing assignment, the assignment where we tell it to serve the new request, and the instruction to reposition to each possible charging station in our instances. And by doing this, it lets us scale these instances up, right? Because if we add a new vehicle to our fleet, all we have to do now is, at each state, we're going to make an additional prediction. And we'll see an example of this here pretty soon. So I'm going to talk just briefly about how we establish the static bound for this problem. So in order to make this problem deterministic, to establish this bound, we're going to give our decision maker access to perfect information, which means that they know ahead of time exactly who is going to make a request where and when. And in order to solve this problem, we're going to use Benner's decomposition, which involves the use of a master problem and a subproblem. This master problem is responsible for assigning requests to the vehicles and making sure that this is done in a time-feasible manner. And then solutions from the master problem are passed to the subproblem, which ensures energy feasibility and will provide charging decisions, charging instructions for these vehicles. So, if we have a solution that looks like this, from our master problem, we have 3 vehicles and 5 requests, and we pass this solution to the subproblem. It's going to say, okay, vehicle 2 needs to charge its battery to full before it goes off and serves request 3. And by the way, this back-to-back assignment of requests 2 and 4 for vehicle 1 is infeasible. And so we'll add a cut to the master problem, and we iterate until we have an optimal solution. Okay, so now let's take a look at our numerical results. So we're using instances that we've tried to make as realistic as possible. We're using data that's available for the island of Manhattan. So we're drawing on a big trip database that's available for free from the city of New York that contains all of the taxi trips and all of the ride-hail trips for the year 2018. We have the set of all charging stations on the island. and we're going to assume that our vehicles look approximately like a Tesla, mid-range Tesla Model 3, so like 62 kilowatt hour battery, and we assume that these things move at like 11 miles an hour. We're going to look at sort of three classes of instances here. So we're going to look at the first class, which has 1,400 requests per day with a fleet size of 43. And for that, we have a set of results that includes all of our policies, as well as this deterministic bound. And then we're going to look at a more realistic ratio of requests to vehicles. So this is a rather high ratio of vehicles for the number of requests. And so if we look at a more reasonable number, it would be something like 14. So this problem is more difficult to solve in the deterministic case for some reason. And so for that, we do not have the bound, but we will show the set of policies. And then we're going to try to scale up these policies to an instance size with 14,000 requests and 140 vehicles. And for that, we can use our full control agent directly. And so we can just directly evaluate this thing on an instance that's quite a bit larger. But the same is not true of our assignment agent. And so the assigner agent is absent from that analysis. Okay, so what we're going to be looking at are charts like this, where along the x-axis is basically the amount of training that our agents have seen. So we're going to start here, and they haven't seen anything. And then eventually they will accumulate more and more experience. On the y-axis here is the objective. So this is the revenue earned per day by our agents. And for this first class of instances, we see that after about 150 episodes, so this is about 5 months worth of data, both of our deep reinforcement learning trained agents are outperforming our nearest heuristic. So this was promising. If we look at this thing sort of in expectation, so after training has stabilized, we're going to just grab a sample of episodes from deep in the training horizon and see how these things do in expectation. And what we find is that it sort of matches what you see in the picture. But when we look at the perfect information bound, we see that there's a fairly sizable gap here still. So there's certainly room for improvement, perhaps in our policies or perhaps in tightening the bound. So this is on our to-do list. See if we can close this gap a bit. So now we'll look at the instances with a more realistic ratio of vehicles to requests per day. And the results are fairly similar, except now our full control agent is handily outperforming all of the other agents that we've constructed. And again, if we look at a sample of episodes from deep in the training horizon, we find that in this case, since we don't have a fixed bound, we're going to compare against our heuristic here, and we find that our full control agent outperforms it by a little over 19%. And lastly, we're going to look at this set of instances where we've now dialed up the size by a factor of 10. So we now have a fleet size that is 10 times larger and a number of requests, a request density that's 10 times larger. And now we're not doing any training. So there's no real consistency along the x-axis here. These are just a batch of experiments. And what we see is that our full control agent, despite having never seen instances of this size before, is still our best performing policy. The gap is smaller to the nearest heuristic than it was for the smaller instances, but it still earns about $6,000 more per day, or about 5% better than our heuristic. So in conclusion, we've had some success using deep reinforcement learning to train an agent that is currently our best performing policy on this problem. We've seen some evidence that this agent scales. We're currently in the process of shifting. So in theory, there's no reason why we can't dial this all the way up to a real life sort of Manhattan style instance where we have 450,000 requests a day and 4,500 vehicles. I don't have those results to show you, but I can tell you that our initial tests suggest that action selection with the neural network still happens very quickly in this case. So it's only taking like a 20th of a second to generate an action for a fleet size of 4,500, which is exciting. But we'll see if the performance scales. That's the important part. And then we have some to-dos, right? So this is a relatively new project. So we'd like to improve benchmarks, both deterministic or maybe increase, tighten the bound, and dial up instance size. And then real quick, I'll put a plug in for TSL next May. I don't have the slide, I'm sorry, but everybody should attend. And then I'd also like to make a plug for tomorrow morning if you're interested in more deep reinforcement learning applied to vehicle routing style problems. There's an interesting session at 8 a.m. And with that, I'll take questions.